this year. So this is from Band Red, which is an awful anime. I don't know why I watched it.
For science.
So I'm not going to show a clip for this one because the clip is just so long and it doesn't really do much. But the bad guys are surrounding our good guys, and what do they do to escape the bad guys? They hide in a planet, like a Jupiter-type planet, a gassy planet. And they go, oh, well, it's a planet that's about to become a star. Well, obviously, they suck at astronomy, too, because planets don't turn into stars. That's kind of the characteristic of the planet, that it doesn't have enough mass to be a star. So, obviously, they don't know what they mean, but if it's about to become a star, what they really are meaning to say, maybe it was a bad translation, is protostar. So we'll go with they're hiding inside a protostar, a big cloud of gas that's condensing into a star, but that hasn't started fusion just yet. So they hide inside a protostar to escape from the bad guys. But still, the bad guys are surrounding an entire star, so how do they escape this? Well, they shoot the center of it with a laser, and they cause the star to start fusion, and then they fly out of it really fast before the bad guys catch on that the star is about to start fusing and blows up on them, or something. Right, it was pretty bad. Right. So what I wanted to know is, okay, can you really do this? How big does something this big have to be? So let's put this in a bit of perspective. In that, as they were getting to the center, they go, the pressure outside is 2.31 gigapascals, whatever that means. So what I really want to start off with is that if at the center of this star, that's the supposed pressure, let's compare that to a real protostar. So a protostar, as we say, it has to be able to do fusion of some sort. The easiest fusion to do, lowest temperature, is using deuterium, which is hydrogen with an extra neutron stuck in there. It's just easier to fuse. And you can do it at this mass here, which is about 12 times the mass of Jupiter. So that's where we get that. So the radius actually turns out to be about the same as Jupiter, so it's about this. And the density, well, mass divided by volume, you can go ahead and figure out what the average density is. So it's about 1,600 kilograms per cubic meter, which is really, really dense, oddly enough. So anyway, a real, why is there a thingy at the bottom? Weird awkward thingy. We'll get there. Ignore that for now. Real stellar interior. What we want to do is use this equation here. We want to look at the pressure gradient. How does pressure change as you go from the center to the edge? Well, at the very center it's going to be high, and at the very edge it's going to be 0. In contrast, your radius is going to be 0 at the center and go up to a number at the outside. So we can kind of cancel some of this stuff out by just making the pressure at the surface 0, the radius at the center 0, and it simplifies to this very nice little negative P over R sub S. And we want to set this equal to the equation of hydrostatic equilibrium, which is a bad thing to actually do in this case because it's not in hydrostatic equilibrium. It should still be contracting, but on short time scales, what's that among friends? So we set this all equal, and now we have suddenly a whole bunch of the variables that we know what they are. We have the pressure, we have the radius of it, we have the density. So let's go ahead and start doing some calculations here. What we want to do is calculate the real pressure at the center of a real protostar. So now that's where that should come up. And the real pressure at the center of the star is 1.6 times 10 to the 17. So much, much higher. So let's put it on a graph here, because graphs are great when you're doing science. So on my y-axis, I put the pascals, the pressure. On R, I have put the radius. What I'm going to do here is kind of plot roughly what the graph should look like for your pressure versus your radius. And just very quickly, we know these two things. We know what the pressure is at the center of the star. We just calculated it. We know it's 0 at the edge of the star. We said it's the same mass as Jupiter. So we have 2 points. From 2 points, you draw a line. From a line, you can get an equation. And now I can use the pressure that they gave me to put on this line and figure out where in the star they really were shooting it with lasers. Turns out, this isn't a perfect thing because obviously as you have more and more layers, it's more and more pressure. So it's really going to look like that. But let's see if it matters, because here is where they are. They are still on the surface of the star at that pressure. So even though the graph is kind of not quite right, it's so close there, it doesn't matter. They are not at the center of the star. They're shooting the surface with lasers while they're in the atmosphere. So I don't know how the bad guys fell for that one. All right. So let's do some